Phase noise, phase jitter. Phase jitter is the term. Phase jitter is the term used for looking at the phase fluctuations themselves. That is the deviations in the position of the phase against what would be expected from a poor signal at any given time. Accordingly, the phase jitter is measured in radians. The phase noise or phase jitter is of particular importance because it reduces the signal quality and hence increases the error rate of the communication link. So here typical phase noise spectrum of a free noise amplifier, free running oscillator. Next, while specifying phase noise, three elements need to be specified: phase noise amplitude, the offset from the carrier, and the measurement bandwidth. It is expressed in dB relative to the carrier. This is normally denoted in dBc. Example, minus 70 dBc, minus 70 decibels down in level from the carrier. The offset from the carrier, example 1 kHz, 10 kHz, 100 kHz. Measurement bandwidth. Noise power is proportional to the bandwidth, so it should be always mentioned. Typically, 1 Hz is taken as the bandwidth. This is perhaps the most important parameter in many oscillators and it deserves an in-depth discussion on what it is, how it affects a system, and how it can be minimized in the oscillator design. Most RF system requires an overall integrated phase noise specifications to be met, as phase noise can correct both the up converted and down converted signal paths. General considerations. Assume that the energy restorer is noiseless. The tank resistance is therefore the only noisy element in the model. So, to gain some useful design insight, first compute the signal energy stored in the tank. E sign is equal to half CV square Pk. So that the mean square signal voltage is V square sign is equal to E sign by C, where we have assumed a sinusoidal waveform. The total mean square noise voltage is founded by integrating the resistor's thermal noise density over the noise bandwidth of the RLC resonator. So Vn square is equal to 4kT or 0 to infinity Z of by R square dF is equal to 4kTr into 1 by 4 RC is equal to kT by C. Combining equations 2 and equation 3, we obtained a noise to carrier ratio. So the reason for this upside down ratio is simply one of conversion. Sensibly, n of 1 therefore needs to maximize the signal levels to minimize the noise to carrier ratio. We may bring power consumption and resonator Q explicitly into considerations by noting that Q can be defined generally as being proportional to the energy stored divided by the energy dissipated. That is, Q is equal to omega naught E sin by P dissipation. Hence, we may have written as N by S is equal to omega naught KT by QP dissipation. The power consumed by this model oscillator is simply equal to P dissipation, the amount dissipated by the tank loss. The noise to carrier ratio is here inversely proportional to the product of resonator Q and the power consumed, and it is directly proportional to oscillation frequency. Oscillations generally operate in one of two regimes that may be distinguished by their differing dependence of output amplitude on bias current, so that one wave right V sin is equal to I bias into R, where R is a constant of proportionality with the dimensions of resistance. This constant in turn is proportional to the equivalent parallel tank resistance, so that implying that the carrier power may be expressed as P sin is directly proportional to I square bias or tank. The mean square noise voltage has already been computed in terms of the tank capacitance as Vn square is equal to Kt by C, but it may also be expressed in terms of the tank inductance. Vn square is equal to Kt by C is equal to Kt by 1 by omega naught square L is equal to Kt into omega naught square L. An alternative expression for the noise to carrier ratio in the current limited regime is general considerations. An alternative expression for the noise to carrier ratio in the current limited regime is therefore N by C is directly proportional to Kt omega naught square L by I square bias into R tank. Only the tank inductance and resistance may be practically varied to minimize the N by C ratio. That is, optimization of such an oscillator corresponds to minimizing L by R tank. So, what are the circuit examples? There are two circuit examples that are RLC oscillators and number two ring oscillators. So, having derived expressions for the phase noise at low and moderate offset frequencies. It is instructive to apply the insights guide to practical oscillators. The popular Colpitts oscillator and its relevant waveforms are shown in the figures. An important feature is that the drain current flows only during a short interval coincident with the most benign movements. Example, the Colpitts oscillator is given. So, an approximate incremental tank voltage and drain current for Colpitts oscillator is shown. Its corresponding excellent phase noise properties account for the popularity of this configuration. It has long been known that the least phase noise occurs within a certain narrow range of tapping ratios. Example 3 is to 1 or 4 is to 1 C2 by C1 capacitance ratio. A common configuration that does so is Clapp's modification to the Colpitts oscillator as shown in the figure. So, an circuit example for HC oscillator, Clapp oscillator and Colpitts oscillator, both configurations should be here taken. So, differential implementations of oscillators with tapped resonators have recently made an appearance in the literature. These types of oscillators are either of Clapp configuration or dual. The Clapp configuration becomes increasingly attractive as supply voltage scale downward, where conventional resonator connections lead to VDD constrained signal swings. Use of tapping allows signal energy to remain high even with low supply voltages. Simplified schematic of the VCO in Margaret L. LC oscillators. A simplified schematic of this oscillator is shown in the figure. A tapped resonator is used to increase the tank signal power. The optimum capacitive tapping ratio is calculated to be around 4.5 based on simulations that take into account the cyclostationarity of the noise sources. Consider a ring oscillator as shown in the figure. 5-stage ring oscillator with identical noise sources on all the nodes. So, ring oscillators. First, the resonator Q is poor because energy stored in the node capacitances is thrown away from every cycle. So, if the resonator of a Colpitts oscillator may be likened to a final crystal wine glass, the resonator of a ring oscillator is mud. Next, energy is restored to the resonator during the edges rather than at the voltage maximum. As a consequence, ring oscillators are found only in the most non-critical applications or inside wideband PLLs that clean up the spectrum.